For our third tool of structural mechanics, we need to enforce compatibility. Now remember, for the fix bar, that always is going to be the same thing. It means that the total twist is equal to 0. So compatibility says that the twist of the right-hand end relative to the left-hand end is equal to 0. That means that the twist in bar 1, which is theta of B relative to A, plus the twist in bar 2, theta of C relative to B, is going to be equal to 0. Now, what we really know is that point B is twisting one way. But if you look at the relative displacements, then we realize that one is twisting in one direction relative to the other, and the other is going to be going in the opposite. So clearly these are going to be equal and opposite if we look at the right-hand end, or I should say the bottom end relative to the top end. So there is a fact that they're basically going to cancel each other out. So let's go ahead and substitute in then now our strain displacement relation. So we can put in our TL over JG that we had from our earlier discussion at the end of part A for this particular lecture. So if we do that, then let's go ahead and write these things out. That's going to be R1 times 12 divided by pi over 32, 1.5 to the 4th times 3.7 times 10 to the 6th, plus the theta of C relative to B. That's going to be R1 plus 12,500 times that length, which is 18, divided by its J, pi over 32, times 2 to the 4th, times 5.6, times 10 to the 4th. And that all has to be equal to 0. Now notice what happens. That is one equation and one unknown. We have used interior statics. We have used the stress strain law, TL over JG, and now we've enforced compatibility. So this gives us one equation and one unknown. So we've set this problem up where we had to use all three to get to this particular point. At this instant, it's useful to point out that a lot of us, when we're engineers and we're just used to doing things, we might look at this and we're being very tempted to go ahead and say, let's calculate J for that first segment AB, and then let's calculate J for segment BC. And so we always want to do that first. If we've got a particular way of doing things, and that might be useful for us. But I want you to notice something. A lot of times in SI, things are going to cancel. So in statically indeterminate problems, a lot can cancel. And that's going to eliminate our calculation. So for example, if I multiply through the top and the bottom by pi over 32, notice this is gone and this is gone. That saves us some calculator punches. Also the 10 to the 6th, that's common. So I can get, whoops, that should have been 10 to the 6th, my mistake. I don't know why 10 to the 4th came out. So the 10 to the 6th then is also going to cancel. So that makes things a little bit simpler, and it's easier for us to go ahead and write all of this stuff out. All right, if we do that, then what we're going to find is if we multiply through by that common factor, then we're going to get the following. We're going to solve this. So again, you're going to have R1 on one side, and you're going to pull this over to the other side. So you're going to get a negative. And you're going to find when you solve that R1 is equal to negative 2.984. I guess it's, I should say, change that to pound inches. So negative 2984 pound inches. In other words, the internal torque is going the other way. We assumed that it was going one way and we guessed wrong. So that means physically, the torque in bar AB actually goes this way. It's 2984. And then the same thing with, if we add that into the second segment for BC, then that turns out to be, we have to add 12,500. And then that does give us, so let's go ahead and do all of this stuff. Like so. like so. Then if we, and again, we've got our R1 going this way. So the true physical direction in this is going to be going this way. So we have the internal reaction, if we flip around the sign, then it's going to be going in the opposite direction. And again, the reason for that is R1 is equal to negative 2984. So you can also draw it this way, 2984. So 2984 going this way is the same as this way with a negative sign in front of it. All right, then we can also do the internal bar force. Let's draw this, let's do it this way, 2984. And then we have 12,500. This one actually goes this way then. So if we do that statics, we get R1 plus 12,500. So we basically subtract them and we get 9516. These are both in pound inches. So those are the physical directions then of our internal torques that we've got here. Now it turns out that for this problem we're not asked to solve for the angle of twist. All we need to do is find the stress in each segment. So for the segment AB, so tau AB max, we're going to use the value of T rho over J for that segment that gives us the biggest one. And remember, that's going to be where rho is at a max. So the numbers that we're going to put in are 2984, and it doesn't matter what your sign is. Remember, all we care about for these particular problems are going to be the values, not the signs. So the value of rho is half the diameter, so that's 1.5 divided by 2. All divided by J, and that's going to be, now we can't cancel it out, that's going to be pi over 32 times 1.5 to the fourth. And that turns out then to be equal to 4503 PSI, or now since our original problem, the load was given to us in kip inches, we could say that tau AB max was equal to 4.503 KSI. Now, notice in pictures, notice the direction of the torque. That means on the underside of the section, we could draw it like this. So I'm looking at it from the bottom up, and for this direction, notice the double arrow is going that way. So I put my thumb that way. So the thumb is going up, and that means that I've got the torque is sweeping around this way on the underside. Like so. So that's going to be the underside. My right hand rule, if I orient this, and I put my thumb on it, that's the direction of tau. So 4.503. And this is the underside. This is the underside of my segment AB. So that's what the field of arrows looks like as I'm going around that way. BC, similar. So tau BC. I now have T rho over J for that particular segment. That's going to be 9516 times its maximum radius. That's the diameter divided by 2, all divided by J, which is pi over 32, 2 to the fourth. And that's going to give 66058 PSI. So if we wanted to give this in terms of the input forcing function, we would say that tau in BC max is equal to 6.058 KSI. And now notice for this segment, notice the right-hand rule is going to be down. So I'm going down. That means it's going to be the opposite. So if I have, let me draw this a little bit larger. And now I've got, oops, like so. And now my double arrow is going downward, so that means it's going in this direction. And there's 6.05 8. So I'm looking at the underside of segment BC, and notice it's going in different directions now. I have along the edge closest to me, I'm going from the right to the left, versus here where I'm going from the left to the right. So it changes direction. So notice tau changes the direction. And that's perfectly acceptable. It's all going to be based on what the value of the torque is and how that's going to be divided in between the particular segments. Now notice that for this problem, we were not asked to find the value of the twist. And that's a common thing. Finding the twist is a common thing. So what if we wanted to find theta of B? What would that be? Well, the first thing that we notice about that is it's going to be going in this direction. So and that makes sense, doesn't it? Because if we put our applied torque, notice it's going this way, we would certainly expect that this point, that's B, we would certainly expect that theta B would follow the torque. So we know that, and we could use our TL over JG for that particular segment. So we would go back and we would say theta of B is equal to the torque, that's 2984. The length segment that we've got there is going to be 12, divided by the J, pi over 32, times 1.5 to the fourth. And then the G value that we had for that, remember that was 3.7 times 10 to the fourth. No kidding, 6, like so. And we would punch that number out, and that would be that number, which I didn't bother doing, radians. And notice now it would be in this direction. So we don't say clockwise, counterclockwise. We don't do this. In my opinion, that's terrible. If you use the right-hand rule and orient your thumb this way and say that's the direction of the twist, that's a lot easier to see for that segment. So notice that theta at B follows the applied torque. And that punches out the end of this example and the end of part B.